Okay, let's get rolling today. First thing you may have noticed when you came in is that there's a flyer on the board for Alpha A to Alpha, which is one of the many pre-health organizations on campus, and they have their last meeting, I guess that would be this week, Wednesday. Another reminder about Wednesday, I'll send an email about this for people that aren't here, but remember that on Wednesday we're doing the course evaluations as well as a bonus quiz that's just participation only, so you get full credit if you're here and you do that. So please come on Wednesday if you're able to. And then what we're going to do today is we're going to start, believe it or not, the very last chapter that we're going to cover in this course, which is Chapter 9. Chapter 9 is kind of a bit of a hodgepodge. There's a lot of different things going on here, but they're all related to condensed phases. So we just finished talking about gases and all kinds of different properties and processes involving gases, and then Chapter 9 we're going to close with the other two phases of matter, liquids and solids, and especially talk a lot about solid phases. All right, so if we think about what we learned very recently in class about gases, last time we talked about the assumptions of the kinetic molecular theory and how they sometimes break down with real gases. So the kinetic molecular theory, again, it tells us the properties of gases when they're what we call ideal gases. And one of the key assumptions, there's really two key assumptions of the kinetic molecular theory that are not really true. One is that the gas molecules themselves have no volume, which we recognize is pretty false, obviously. But then the other is that there's no forces of interaction between the gas molecules. And this is another one that sort of breaks down. And then in reality, there are forces of interaction. And what we're going to talk about in Chapter 9 at the very beginning are what do those forces look like when atoms and molecules are packed close together. What are the forces that hold them together in these condensed phases, liquid and solid? All right, so that was one of the key assumptions that we're going to break down today, which is that the particles have no interactions with each other. And in many cases, this is not a horrible assumption. So if we have, as we talked about, high temperatures or in low pressures, big volumes where the gas molecules are very spread apart, then the interactions between them are very small and very minor, so we can assume that they're nothing. But as we start compressing the gases, we start making the volume smaller or cooling the temperature or some combination of those two, and the molecules get closer and closer together and spend more time interacting with each other, there's going to be contact between those particles and there's going to be forces of interaction between them. So in real gases, which are the ones that deviate significantly from the ideal gas law, as well as liquids and solids, which is the topic of this chapter, in reality, atoms and molecules are in constant contact. And there are going to be interacting forces that hold them together. Okay, because the key difference between solids, liquids, and gases is in gases, the molecules and atoms are moving around freely. They're flying around through space at very high velocities, as we've been able to calculate. And in liquids and solids, though, there is still some motion, of course, but the molecules and atoms are in close contact with each other. And the reason they remain in close contact is because of these interacting forces between them. So really the first topic that this chapter deals with, and the first thing that we're going to talk about, are the types of forces that hold atoms and molecules together in condensed phases. So first we need some general definitions, and we have to understand what it means to be an intermolecular force. So that's kind of the big umbrella term that we use for all of these forces between atoms and molecules, intermolecular. And if any of you are Latin scholars, or if you took Latin in high school like I did, wouldn't call myself a scholar, but there's the difference between inter and intra. So inter means between. So when we're talking about intermolecular forces, we're talking about the forces between two or more atoms and molecules, between collections of atoms and molecules. Whereas intramolecular deals with the forces that are within an individual molecule. All right, so there's the difference between inter and intra, which of course look very similar, but they mean different things. And so intermolecular forces are forces of attraction between two molecules. And then obviously if we have larger than a collection larger than 2 molecules, there's going to be forces between all of those. Now, the word has intermolecular, has the word molecule in it, but it doesn't have to be just molecules we're talking about. There's also intermolecular forces between atoms. There's also intermolecular forces that involve ions. So really, more generally, between 2 particles. Where, again, we recognize the definition of particles that we're considering are things like atoms, molecules, ions, the components of chemical matter. So that's what we mean by intermolecular forces. Now, it's important to distinguish intermolecular forces from other things that we've learned about in this course, which are primarily intramolecular. So when we talk about intramolecular forces, we're talking about bonds between atoms. So intermolecular forces have nothing to do with the individual bonds that hold atoms together. So those intramolecular forces are things like covalent bonds, ionic bonds, things that are actually holding atoms together in compounds. We're not talking about that when we're dealing with intermolecular forces. And so we don't want to try to equate intermolecular forces to covalent bond strength. They really have nothing to do with each other. They're 2 separate topics. So these covalent bonds, or really any type of bond that we've dealt with before, these are what we call intramolecular forces, and they're a different concept. And we don't want to try to confuse the two or relate the two in any way. All right, so maybe to put it a little bit more simply, let's say we have a water molecule, H2O. One very familiar with us. We're going to have 2 oxygen-hydrogen bonds, and those bonds are what we call the intramolecular forces. They're holding the hydrogen and oxygen together to make that water molecule. But then the individual water molecules in a sample of water, this H2O, that H2O, all the ones that are around each other, are going to have forces of attraction between them. Those are the intermolecular forces, and that's what's responsible for water existing as a liquid. But it has nothing to do with the individual bonds between oxygen and hydrogen. They're forces that exist between the molecules themselves, and that's what this topic, this section of the course is going to deal with. Now, before we get into intermolecular forces in more detail, we have to talk a little bit about phase changes, because what we're going to see is that the primary property of substances that we're going to relate to these intermolecular forces is going to be their phase change properties. So just like everything in chemistry, we have these atomic and molecular phenomena that are happening at the microscopic level, and we're going to relate those to some bigger macroscopic property. And the property that's most closely related to intermolecular forces, the one that we're going to talk about in probably the most detail, are what are called phase changes, which is the change from solid to liquid to gas and so on. So there's 2 types of phase changes we need to be familiar with. The liquid to gas transition. If we're going from liquid to gas, we call that boiling. And then if we go in the other direction, if we have a gas and we condense it to a liquid, we call that condensation. All right, so the terminology is different depending on which direction you're going, from liquid to gas or from gas to liquid, but it's just the interconversion between liquid and gas phases. And then what's most important is the temperature at which this process happens. Now in Chem 2 you'll learn a more precise definition for these different temperatures, but for our purposes the boiling point is the temperature at which the liquid and the gas interconvert. All right, so we all know that water exists as a liquid at room temperature, and then if you put it on your stove and boil it up, once you get to 100 degrees Celsius, the gas phase becomes the more favorable phase, and your liquid water is going to be converted into gas phase water. And so that's what we talk about when we're referring to boiling. And the boiling point, the temperature at which this happens, is going to be related to the intermolecular forces between the molecules in the compound or the element. And then the other phase change we want to be concerned with is the liquid to solid conversion. For going from liquid to solid, we call that freezing. We don't have to deal with that too often in Houston. And then the other direction, if you're going from solid to liquid, is called melting. Usually the temperature at which this occurs is referred to as the melting point, although sometimes you'll see it called the freezing point, and they're really the same thing. And of course for water this occurs at 0 degrees Celsius. But this is the temperature at which the liquid and the solid interconvert. We'll have a lot more details about phase changes towards the end of this chapter. One of the last things we'll talk about, maybe the last thing we talk about. But for now, we just want to be aware of what they are and that there's a temperature that defines each of them. Liquid to gas is the boiling point. Liquid to solid is the freezing or melting point. And these temperatures are going to be what we relate to these intermolecular forces, or how we sort of rationalize the differences between them. So the key point then, this relationship that we're going to see as we compare intermolecular forces, is that stronger intermolecular forces which I'll abbreviate as IMFs. Let me rewrite that, sorry. That's going to correlate with a higher boiling or freezing point. Okay, so if we compare two substances, let's say water and then acetone, which is what's commonly found in nail polish removers, water has a higher boiling point than acetone. Acetone boils around 50 degrees Celsius, 56 I guess it is, and water boils at 100. So because water has a higher boiling point, that means it has stronger intermolecular forces. But the question that we need to start learning how to answer is, how do we predict which substances have stronger intermolecular forces than others? What are the factors that govern which intermolecular forces we have in a specific substance, and whether one is stronger or weaker than another? So for that, we need to start defining the types of intermolecular forces that exist, and then sort of figure out which ones are stronger and weaker, and then what factors influence which of those are going to be the stronger or the weaker of the pairs. Okay? So there's going to be three different types of intermolecular forces that we're going to primarily deal with. Two of them are very closely related. But the first one is what we call London dispersion forces. And the question that we first have to answer is, what kind of compounds or what kind of substances have London dispersion forces? And this one's, in some sense, the easy one, because everything has London dispersion forces as a type of interaction between the molecules. So anything with electrons is going to have this type of interaction, London dispersion forces. As we'll get into, London dispersion forces are the weakest of the intermolecular forces. So these are very weak attractive forces. And then why do they exist at all? They involve what are called instantaneous dipoles. And we're going to draw pictures of what that means here in a second. All right, so why would two things that are, why would two neutral atoms or neutral molecules, why would they interact with each other at all? Why would they have any sort of attractive force between them? And it's this concept called instantaneous dipoles, which we have to start thinking about and try to understand at an atomic or molecular level. So let's say we have two atoms that are interacting with each other. Let's say helium, for example. Now we know from our discussion of atoms that the electron density around an atom is largely spherical, especially for something like helium that has a 1s2 valence configuration. So the two electrons exist in a spherical s orbital. They're distributed evenly around the nucleus. So we wouldn't expect any unequal distribution of charge for a helium atom. There's if we have two helium atoms next to each other, they both have spherical electron densities. They're both neutral. You wouldn't expect there to be any regions of positive or negative charge. But what this instantaneous dipole implies is that as two atoms become close to each other, the nucleus of one atom starts attracting the electrons of the other atom and causes sort of a distortion of the electron density that exists for a very short period of time. So we can draw this like this. For some very short instant, the electron density of these are going to be distorted. So basically the white oval or circle that I'm drawing represents the electron density. And so the electron density gets distorted, and you're going to have then small regions of delta minus and delta plus. Now we talked about polar molecules earlier, which have permanent dipoles, where there's permanently a region of partial negative and partial positive charge. Even in things that are nominally non-polar, like an atom, you can have what are called instantaneous dipoles, where just for a brief instant in time, the electron density distorts, and then you have sort of this region delta minus, delta plus, and then you're going to have a weak force of attraction between them because of that distortion. Now, overall, on average, if we were to watch a helium molecule over a period of time, overall it's nonpolar because the instantaneous dipoles average out over time to be zero. But for some brief instant, there's going to be this distortion that's going to cause an interaction, and then for some other period of time, the electron cloud could distort in the other way, where the delta minus and the delta plus sort of switch sides, and you still have this interaction between them. So on average, there's no polarity involved. There's no permanent dipole. But because of these small distortions that happen over time, there's always going to be some small force of attraction between those atoms. All right? So that's what's going to give us these London dispersion forces, and the same thing happens in molecules. So let's say we have a perfectly nonpolar molecule like Br2. All right, whenever we have two of the same atom bonded to each other, it's nonpolar, as we've talked about. So again, in this one, you would expect a very symmetric electron density. It's not spherical anymore, but there's no partial negative or partial positive charges on average because the two atoms have the same electronegativity. So if you bring two bromines in close contact with each other, you wouldn't expect there to be a real strong interaction. There's no permanent dipole. But again, these electron densities can distort periodically, and you have these instantaneous dipoles. All right, so this one's a little bit tougher to draw, but you could have a slight distortion of the electron density, where you'll get, again, an imbalance of the charge, where there's more electron density on one side than the other. And if the opposite sides line up, delta plus, delta minus, you get these weak forces of attraction between them. And then the electron density can distort in the other way, where you'll have delta minus and delta plus. Delta plus, delta minus, and again, a force of attraction between the opposite poles. All right, so there's no permanent dipole in Br2. On average, it's nonpolar, and there's no unequal distribution. But for brief snapshots in time, the electron density gets distorted by a nearby molecule, or just by chance, because we know that the orbitals that these electrons sit in are probabilistic. The probability density for Br2 is going to be symmetric, but at some instant in time, because it's a probability, and not because it's not a actual picture of the electron density, at some period in time there's going to be a distortion, and that distortion is going to lead to imbalances of charge, which lead to these small attractions. Now, I emphasize that this is a very weak interaction, and that these distorted instantaneous dipoles, as we're calling them, are only fleetingly active. They're not there all the time, but for brief instances in time, you're going to have this, and that leads to those attractions. So that's what we call London dispersion forces, and the important point is that everything has these types of interactions, because everything that has electron density at some point in time is going to have perhaps a distortion of the electron density that can lead to these weak forces. Now let's talk about the factors that influence the strength of London dispersion forces. So let's look at all of the noble gases. For anything that's atomic species like a noble gas, or anything that's a nonpolar molecule, London dispersion forces are the only types of interactions between them. And let's look at the boiling points of these and see how they compare. So this is going down the periodic table. Helium is the lightest noble gas. Radon is the heaviest noble gas. Let's look at how the boiling points changes as we go from top to bottom. Okay, so helium has a boiling point of 4 Kelvin, very, very low. If you've ever, liquid helium is extremely cold if you've ever worked with it. So 4 Kelvin is the boiling point of helium. Neon, it goes up to 27 Kelvin. Argon, 87 Kelvin, 121, 165, and 211. So we see a pretty steady increase in the boiling point as we go from the lighter noble gases to the heavier noble gases. So the conclusion we can draw from this is that London dispersion forces are stronger when there are more electrons. And this means when they're, when the atoms or molecules are heavier. All right, so as we go to heavier and heavier species, the London dispersion forces are going to get stronger and the boiling point and the melting point is going to increase. And this relates to a concept called polarizability. So again, these nonpolar species, things like noble gases or nonpolar molecules like Br2, they don't have net dipoles, but they do have what's called polarizability, which is the ability of the electron cloud to distort. So what we're really saying here is that the heavier atoms and molecules are more polarizable. The more polarizable they are, the stronger those instantaneous dipoles are going to be. Now the question becomes, why are heavier atoms and molecules more polarizable? And this relates to something that we talked about very close to the beginning of the course, which is that as you have electrons that reside further and further away from the nucleus, remember as we add more electrons, they go into orbitals that are further and further away from the nucleus, those outer electrons are going to be held less tightly. So in larger atoms and molecules, the outer electrons are held less tightly. That makes them more polarizable. They're easier to distort. So because the outer electrons are held less tightly, the heavier atoms are more polarizable. Another way to think about this is quantum mechanical, which is probably not everyone's favorite way of thinking about things, but remember that as we talk about radial probability distributions for orbitals, as we go from, let's say, 1s to 2s to 3s to 4s, as we would be for the valence electrons, or 1s and then to 2p and then 3p, 4p, 5p, and 6p. As we go to farther and further subshells, we have larger radial probability distributions, which means that there's more of a probability of the electron cloud being distorted at any given time versus one that has a very small radial probability distribution where the electrons tend to stay very close to the nucleus. So there's a couple of different ways of thinking about this concept of polarizability, but the idea is that the heavier ones are more polarizable, which means they have stronger London dispersion forces. Okay? So that's how we deal with. So let's just look at a sample problem. Rank the halogen molecules from lowest to highest melting point. So this one is exactly the same concept as we saw for the noble gases. Halogens are diatomic, as we should know. So those are going to be F2, Cl2, Br2, and I2. I think there's one more, acetine, but that's radioactive, so we're not going to worry about that. So let's compare these four common halogens, fluorine, chlorine, bromine, iodine. So the two key concepts here are that stronger intermolecular forces correlates with a higher melting point, also a higher boiling point if we were comparing boiling points. And then these are all nonpolar molecules, so the only intermolecular forces we have to consider are these London dispersion forces. And as we said, these are stronger and heavier elements. And so what that means is that we have the order coming in exactly this order. So this is the lightest halogen, this is the heaviest, and the boiling points are expected, in this case the melting points are expected to track in that order. So fluorine the smallest, chlorine, then bromine, then iodine. And if we think about the physical states of the halogens, this makes a little bit of sense. So F2 is a gas. It has the weakest intermolecular forces. It exists as a gas at room temperature. Cl2 is also a gas, but it's a little bit easier. It would liquefy at a higher temperature. And then if we go to these heavier halogens, Br2 exists as a liquid at room temperature. It has stronger intermolecular forces, so its standard state at room temperature is liquid phase. And then iodine has even stronger intermolecular forces, and it exists as a solid at room temperature. So we can see that just by comparing the states of matter for the halogens, this idea of the heavier ones having stronger London forces sort of makes sense. All right, but like I said, that's the weakest one. It's extremely weak compared to covalent bonds. But let's talk about then the next type of force that we're going to deal with, which are dipole-dipole forces. Just to give you an idea, these are around 1% as strong as covalent bonds. All right, so we've talked about this difference between intra and intermolecular forces. Intermolecular forces tend to be much weaker than the individual bonds that hold things together. So even if we have these dipole-dipole forces, they're only about 1% as strong as the covalent bonds that are holding the molecules together. But then which molecules have this second type of force, dipole-dipole? It's any polar covalent molecule. All right, so for dipole-dipole forces to exist, we have to have a permanent dipole moment, something that actually has permanent polarity. And this, of course, also means we have to have net molecular polarity, not just polar bonds. So in Chapter 4, we talked about the difference between bond polarity and molecular polarity. And the only types of molecules or compounds that have these dipole-dipole forces are ones that have net permanent dipole moments. They can't just have polar bonds, they have to have an actual dipole moment. Alright, so as an example, carbon tetrafluoride, CF4, it has polar bonds, but it's nonpolar, so it would still only exist London dispersion forces. But anything that is polar, anything that has net polarity, would have dipole-dipole forces. So to depict these forces, here it's a little bit more straightforward, because in this case we're talking about polar molecules that have permanent regions of partial positive and partial negative charges. So if we talk about HCl, hydrogen chloride, remember that in this case we have unequal electronegativities between hydrogen and chlorine. So we're going to have a partial positive charge on the hydrogen and a partial negative on chlorine. And then these molecules can sort of line up. So if we put another HCl like this, where we have delta plus, delta minus, delta plus, and then we have, and so on. So we can make these large networks where we align the dipoles, the negative and the positive dipoles, and we have these forces of attraction between them. Alright, so all those forces and all these things that I'm showing with these dashed lines here are attractive forces. So we have these attractive forces between the oppositely charged dipoles, delta plus, delta minus, and so on. But then we can also have, which I'll show in red, some repulsive interactions. So the two delta pluses sort of repel each other, the two delta minuses repel each other, and so on. So these forces are not always just attractive forces. We have these repulsive interactions when the two like dipoles line up with each other. But the point is that when we're in a condensed phase like a liquid or a solid, the molecules are going to line up in a certain way such that the attractive forces are stronger than the repulsive forces, and that holds things together. Alright, so we have both attractions and repulsions, but the attractions win out, and it's because of these oppositely charged dipoles that line up, and we have this force of attraction anytime we have two opposite charges next to each other. Okay, so anything that's polar is going to have these types of dipole-dipole forces, and these are considerably stronger than the London dispersion forces. All right, now there's one other type of dipole-dipole force that we sort of categorize as a third type of IMF. We call these hydrogen bonds. These are much stronger than typical dipole-dipole forces. These can be around 5 to 10% as strong as bonds. So still not nearly as strong as a covalent bond, but much stronger than a typical dipole-dipole force. So really, hydrogen bonds are just a special type of dipole-dipole interaction. And they occur in certain compounds. We'll talk about which compounds those are here in a second. Now, as the name implies, hydrogen bonds exist in compounds that have hydrogen, and it's really going to be only 3 types of compounds that have these types of hydrogen bonding interactions. They either have to have hydrogen-fluorine bonds, which really for our purposes is only HF itself. So HF exhibits hydrogen bonds, Anything with an OH bond will exhibit hydrogen bonds. That's going to be things like water, alcohols, acetic acid. Anything that has an OH bond exhibits hydrogen bonds, and anything with NH bonds will have hydrogen bonds as well. Alright, so if your compound has at least one HF, HO, or HN bond, it's going to exhibit hydrogen bonding, and that's a particularly strong type of intermolecular interaction. So compounds that exhibit hydrogen bondings would be things like HF, water is a classic example, alcohols, something like methanol, CH3OH, ammonia, NH3, all of these exhibit hydrogen bonding. Now, why is hydrogen bonding so much stronger than regular dipole-dipole interactions? There's really two reasons. First of all, we notice that it's limited to only these three elements, fluorine, oxygen, and nitrogen. That's because these are three of the most electronegative atoms on the periodic table. So when you have hydrogen bonded to a very electronegative atom, you have a large polarization of the charge, a very large partial positive on hydrogen, a very large partial negative on the other partner, the more electronegative atom. So you have a very large dipole, and also hydrogen is very small. It's the smallest atom on the periodic table. So when you have these large dipoles that involve hydrogen, they can line up really close to each other. So the force of attraction is determined by not only the strength of the dipole, but also how close they can align. And when you have hydrogen, because it's so small, the molecules compact together very closely, and you have much stronger interactions than you would for other types of dipole-dipole interactions. Okay, so these hydrogen bonds are the strongest type of intermolecular force, and they're only about an order of magnitude less than a covalent bond. Now there are some other types of forces which we're not going to get into a lot of details with these in this course. This is going to be something that you'll see in the first part of Chemistry 2 when you start talking about forces that exist in solutions. We're primarily going to talk about forces that exist in pure compounds, but we should be aware that there are some other types of forces that involve ions that, like I said, we're not going to see the details of these yet, but we should be familiar with them. So there's ion-ion forces, which are what hold the ions together in crystals, which we're going to talk later on about the structures of ionic compounds. So these are the types of forces that are responsible for those structures, but we're not going to really compare them with other IMFs in that standpoint. So these hold ions together in ionic crystals, and these are kind of a gray area. Are these classified as bonds, or are they classified as intermolecular forces? They're kind of, in some sense, both, as we'll see, because when you have an ionic compound, you don't just have interactions between two ions, you really have interactions between ions in all directions. So, for example, in sodium chloride, you'll have Na plus interacting with Cl minus. It's a very strong interaction because you have two oppositely charged species, permanently charged species interacting, but this sodium is going to interact with, I think, 5 other chlorines in all different directions. So there's interactions in all directions. It's not just a localized pair of interactions, so it's kind of in between a bond and the intermolecular forces. But usually we consider ion-ion forces more like a bond than an INF, more of an intermolecular force. So we're not going to really compare it to other intermolecular forces, but be aware that if you have two oppositely charged species, they will, of course, interact with each other very strongly. And then similarly, if we put ions into solutions, so we've talked about aqueous solutions in this course in Chapter 6, if we have a polar molecule and a dissolved ion, we're going to have interactions between those as well. So these are the types of forces that are very prevalent in aqueous solutions, where we have an ionic compound dissolved in water. All right, so when we talked about the process of dissolving ionic compounds in solution, we said that the water molecules surround the ions and break them up and separate them into solution, and the reason is because you have strong interactions between the ions and the water. So water is a polar molecule, as we know. You have a partial positive charge on the hydrogens, a partial negative charge on oxygen, and then this partial negative on oxygen can interact very strongly with the positive charge on your ion, for example, sodium plus. So this type of interaction forms in solution, and then we also have interactions between water and the negatively charged ions. So we have delta minus, delta plus, and this partial positive hydrogen can interact with the negative ion, for example, Cl minus. And these types of interactions are stronger than dipole-dipole interactions because they involve permanently charged ions, Na plus Cl minus, for example, interacting. So they're stronger than these dipole-dipoles where you just have partial positive and partial negative charges interacting. Okay, so this is another type of force that, at least conceptually, is very similar to an intermolecular force, but we're only going to see this in solutions where we have an ionic compound dissolved in some other liquid. So we're not going to really talk about that in this section of the course. This we're going to table until Chemistry 2, whoever you take that with. But it is a type of force that's very much related where you have these charged particles interacting with dipoles in solution, and it's actually stronger than the dipole-dipole interaction that we just talked about. So finally, what's going to be important is the ranking of intermolecular forces, because if we want to compare boiling points and melting points for two substances, we need to know, which one has the stronger intermolecular forces, and we kind of already discussed this, but the dispersion forces are the weakest. And then you have dipole-dipole forces are sort of in the middle. And then you have hydrogen bonding. And these are really the only three we're going to compare for the purposes of comparing boiling points, melting points, things like this. All right, so it's helpful to understand all the details of these conceptually as I just went through, but the most important thing for a lot of the test questions is just to be able to identify them and then rank them in terms of weakest to strongest. And when you're doing these types of problems, I'm going to give you one example here in a second. What you first want to do is identify the strongest intermolecular force that's present, because the strongest force is going to be the one that's the most important. As I said, everything has dispersion forces, so that's always going to be a factor. But if it also has dipole-dipole and or hydrogen bonding interactions, those are going to be the more important ones. So let's do a quick sample problem. Let's say we have CO2 and COS. So CO2, carbon dioxide, and then the molecule COS where you just replace one of the oxygens with the sulfur. Which one has the higher boiling point? All right, so again, what we have to first be able to do is identify the strongest intermolecular force that's present in both of these compounds. So if we think about CO2, remember that we have to determine if it's polar or not first. So carbon dioxide is a linear molecule. We've drawn it a million times. It has the delta minus and delta plus, but because it has a linear geometry, the two cancel out. I didn't draw this particularly well as a linear molecule, but it is linear. So the two dipoles cancel out, and this is nonpolar. All right, so even though CO2 has polar bonds, overall it's nonpolar, and that means the strongest intermolecular force is going to be London dispersion forces. It doesn't have any OH bonds, so it's not going to have any hydrogen bonding interactions. It's nonpolar, so it can't have dipole-dipole interactions. So the only type of forces that exist in CO2 are London dispersion forces. And we should be familiar with CO2 is a gas at room temperature because it has very weak intermolecular forces. Now if we compare that to COS, COS also has a linear geometry, but it has two different outer atoms this time, an oxygen and a sulfur. So there's going to be a very strong dipole going from carbon to oxygen because there's a very large electronegativity difference. But sulfur and carbon have very similar electronegativity. Sulfur is way less electronegative than oxygen because it's lower in the periodic table. So there's only going to be a small dipole going in this direction. So in this case, the two dipoles don't completely cancel each other out, even though the geometry is linear because the two dipoles are different. So you have a net dipole that goes from left to right. And because there's a net dipole, because the two don't completely cancel each other out, this molecule is polar. Now it doesn't have a huge dipole moment because there's still some partial cancellation of its carbon-oxygen dipole, but it's not going to be totally nonpolar. It is polar. And anything that's polar is going to have dipole-dipole forces. These dipole-dipole forces are stronger than the London dispersion forces. Again, we're considering the strongest force that's present in each of these molecules. Dipole-dipole forces are stronger than London dispersion, so this is going to have a higher boiling point. All right, so when doing these types of problems, the only thing you need to worry about is what's the strongest force. This is also going to have London dispersion forces, everything does, but we don't need to worry about that one because we have the dipole-dipole forces that are much stronger and are going to be the more important one to consider. All right, so that's how we sort of approach that. The last thing we're going to talk about are two properties, or a few properties of liquids that derive directly from their intermolecular forces. We're going to talk a lot more about the properties and structures of solids. We're just going to give you a few things to do with liquids here that relate to their intermolecular forces. So the first one is what we call surface tension. Now you're probably familiar with surface tension in your everyday life. There's those, certain types of insects that can sort of walk like they're walking on water because they have that surface tension they're able to stand on. If you've ever gone off a diving board and did a belly flop, you know that it hurts a lot, and that's because of the surface tension of water. So all these things that we're probably familiar with in day-to-day life relate to this property called surface tension, which the precise definition is the resistance of a liquid to increase its surface area. All right, so all liquids are going to have some sort of surface tension because there's these strong forces, not strong, but there's significant forces that are holding the liquid molecules together. And then in order to sort of break that surface and spread the molecules out more, you have to break some of those forces. So there's a little bit of tension at the top of the liquid that's sort of resisting it from changing its surface area. So that's what we call surface tension. And there's a few properties that are related to surface tension. So one of these is called capillary action, or if you're British, capillary action. And this is the spontaneous rising of a liquid in a glass tube. So you'll probably see this in a chemistry lab if you haven't already. It's a very common phenomenon where if you introduce a liquid to a glass tube, the liquid's going to rise up that tube. And this is related to what are called adhesive forces and cohesive forces. So adhesive forces are the force of attraction between liquid and the container. All right, so when you introduce a liquid to some container like glass, which is the one we talk about most often, there's going to be some forces of interaction between the liquid and the container. And if we realize that glass is polar, then it makes sense, because if we have water interacting with the surface of glass, there's these dipole-dipole interactions. Glass has polarity on the surface, water molecules are polar, and so you have these interactions between the dipoles. And then there's cohesive forces, which are what we call intermolecular forces that we just finished talking about. So a synonym for cohesive forces are the intermolecular forces of the liquid itself. So whenever you introduce a liquid to a container, there's going to be this competition between cohesive and adhesive forces. So if you have a situation where the cohesive forces are stronger than the adhesive forces, you're going to get what's called a convex meniscus, where it's going to look like where the surface of the liquid is going to be sort of bowed out like that. This is when the cohesive forces are greater than adhesive forces. And this would be usually what you see in nonpolar liquids, where nonpolar liquids have very weak interactions with the glass because nonpolar and polar things don't interact very strongly. But if you have a polar liquid like water, as you've probably seen in the chemistry lab, when you put water into a glass tube, it gets a concave meniscus, which sort of has this U shape to it. And this is a case where the adhesive forces are stronger than the cohesive. I don't know why this isn't writing properly. So when the adhesive forces are stronger, you get a concave meniscus. And that's because you have stronger forces of attraction between the liquid and the walls of the glass, so the liquid starts to creep up the walls of the glass to maximize those interactions. Okay, so these are some properties of a liquid that are both related to intermolecular forces, surface tension, and then the idea of capillary action and meniscuses that occur when you put them into containers. Now, another important property of liquids is what we call viscosity. You may have heard this in the context of motor oil, but it's the resistance to flow for a liquid. So viscosity is the resistance to flow, and basically you can think of it as how thick the liquid is. That's a very loose definition of viscosity. All right, so if we look at these two liquids here, we see that the blue liquid is flowing very freely compared to the amber colored liquid, which is flowing not so well. So this amber color liquid has higher viscosity than the blue one. So the thicker the liquid, the harder it is for it to pour, harder it is for it to flow. It has higher viscosity. And this also correlates with intermolecular forces. The stronger intermolecular forces correlate with higher viscosity because those forces are going to hold the molecules together and prevent them from flowing freely if you try to pour them or whatever the case is, or try to flow them through another surface. So the stronger the forces in the liquid, the less likely it is to flow, and it's going to have higher viscosity. So as an example, let's predict which of these liquids has the highest viscosity. We have molecules that are all similar in size. We have this one here is a hydrocarbon, just a bunch of carbons and hydrogens. This one has an oxygen in the middle, which if you take organic chemistry, you'll learn that this is called an ether. And then this one here is an alcohol. It has two OH groups on the end. So which one's going to have the highest viscosity is going to be the one that has the strongest intermolecular forces. So if we have hydrocarbons, it might not be as obvious in this case, but these are completely nonpolar. So when you have a hydrocarbon, anything that has just carbon and hydrogen in it, you want to remember that these are nonpolar, and the only types of forces they have are London dispersion forces. Okay, so the strongest force that's present in any hydrocarbon is London dispersion forces. Definitely remember that. All of these are nonpolar. And then if we have this compound here, which has an oxygen in the middle, this one's going to be polar, because if we think about the center oxygen here, we're going to have a bent shape. So much like water, this is going to have polarity because it has a bent oxygen, AX2E2. Dipole-dipole interactions are going to be present. This one does not have any hydrogen bonding, though, because there's no hydrogen bonded directly to the oxygen. However, if we go to this one here, we have two OH groups, so we're going to have hydrogen bonding present. Anytime we have oxygen and hydrogen bonded directly together, there's going to be hydrogen bonding. That's going to be the strongest intermolecular force. So of these three choices, this one on the right has the strongest intermolecular forces, which means we would expect it to have the highest viscosity. And this is something that we call propylene glycol, which is used as a coolant often. It's a very thick liquid if you ever work with stuff like this. All right, so that sort of takes us to the end of talking about liquids for now. We're going to go on next time and start talking about solids in more detail.